The mysterious blue ice of Neptune. Neptune, the eighth and farthest known planet from the Sun, is a world of extremes. Wild storms, supersonic winds, and chilling temperatures, among its many mysteries. One has captured the curiosity of scientists and space enthusiasts alike, the enigmatic blue ice that may lie deep within its turbulent layers. Part 1. Why is Neptune so blue? At first glance, Neptune stuns with its rich, sapphire blue hue, far more vivid than its planetary cousin Uranus, despite their similar compositions. The role of methane. Neptune's upper atmosphere contains methane gas, which absorbs red and infrared light from the Sun and reflects blue and green wavelengths back into space. This gives Neptune its trademark color. But here's the mystery. Uranus also has methane, yet appears pale cyan rather than deep blue. Hidden factors. Recent research suggests aerosols, haze particles, or unknown atmospheric compounds may enhance Neptune's blue tone. The planet's dynamic weather patterns, high-altitude clouds, and vertical mixing may also influence its optical depth and color. In short, Neptune's color may be telling us there's more going on beneath the clouds than we currently understand. Part 2. What does blue ice mean on Neptune? Let's be clear. When scientists refer to Neptune's blue ice, they aren't talking about the frozen water you find in your freezer. On Neptune, ice is a term for frozen volatile compounds, mainly water, ammonia, and methane in exotic high-pressure forms. These ices are not frozen from cold alone, but compressed into new states of matter under immense gravitational pressure. Ice 7 and Ice X, these are types of high-pressure water ices. Unlike the hexagonal ice on Earth, these phases form in the mantle of Neptune under conditions thousands of times more extreme than Earth's surface. Ice 7 forms at pressures above 30,000 times Earth's atmosphere. It is cubic and extremely dense. Ice X forms under even greater pressure. Here, hydrogen atoms lose their identity, resulting in a fully symmetrical, superdense structure. These exotic ices are more like minerals than the transparent crystals we know. Superionic ice, a cosmic oddity. Perhaps the most exciting and mysterious form is Superionic ice. It's first theorized in the 1980s and confirmed experimentally in the 2010s. Oxygen. Atoms stay locked in a solid crystalline framework, while hydrogen ions move like a fluid conducting electricity. It's black in appearance, but in the public imagination, it's often associated with Neptune's deep blue. This ice may form vast interior layers and drive Neptune's strange magnetic field, which is tilted and offset from the planet's rotation axis. This form of ice doesn't exist naturally anywhere on Earth. It's unique to giant planets like Neptune and Uranus. Part 3. The structure of Neptune. A deep dive. Neptune is often called an ice giant, but don't expect it to be a ball of frozen water. Layered interior. Atmosphere. Hydrogen, helium, methane. Dynamic with storms and fast winds. 2. Mantle. A slushy soup of water, ammonia, and methane. Not solid, not liquid, but a supercritical fluid. 3. Core. Possibly a rocky core surrounded by layers of high-pressure exotic ices, including Superionic ice. The temperature inside Neptune reaches thousands of degrees, but the pressure is so great that water and other compounds exist in frozen states regardless of the heat. Paradoxical environment where ice is hot, heat and magnetism. Neptune emits 2.6 times more energy than it receives from the Sun. This internal heat may help drive its violent weather and fuel the movement of conductive ices, which generate the planet's twisted magnetic field. Part 4. How do we know? Most of what we understand about Neptune comes from Voyager 2, the only spacecraft to visit Neptune, revealing its weather, rings, and moons. Ground-based telescopes and Hubble Space Telescope, monitoring storms and seasonal changes. Laboratory experiments, using diamond anvil cells and X-ray lasers to simulate Neptune-like conditions. Computer simulations, modeling pressure, temperature, and phase transitions inside the planet. Still, many of Neptune's secrets remain buried deep inside. It's unreachable by observation alone. What's next? There is growing support in the scientific community for a dedicated mission to Neptune or Uranus. A modern orbiter that could map magnetic fields, analyze atmospheric chemistry, study ring systems, probe the deep interior, search for Superionic ice, and understand its distribution. This would be humanity's first real opportunity to explore the ice giants up close, since Voyager 2's flyby. In summary, the blue ice of Neptune is not just a poetic phrase. It points to one of the most alien, extreme, and fascinating states of matter in the universe. Neptune's vivid color is just the surface story. Beneath lies a world of superionic water, exotic ice crystals, and mysteries yet to be unlocked. It's a reminder that even in our own solar system, we've only just scratched the surface of what's possible in nature.